We all know the basic rule of black holes. Nothing, not even light, can escape. They are the universe's ultimate prisons, cosmic objects so dense that their gravity warps space and time into an inescapable vortex. For over a century, our guide to these strange places has been Albert Einstein. His theory of general relativity predicted their existence and gave us a shocking answer to what lies at their heart, a point of infinite density, where all the mass that has ever fallen in is crushed into a space with zero volume, a singularity. But what if Einstein was only telling half the story? What if this idea of infinity, this point where our equations scream and break down, isn't a description of reality, but a signpost pointing toward a revolution in physics? The true nature of a black hole's core is far stranger and more chaotic, and it holds the key to unifying the two great pillars of modern science, gravity and the quantum world. To find it, we have to take a journey past the event horizon, the universe's ultimate point of no return, to confront the deepest mystery in the cosmos. Because what we find there won't just redefine black holes, it will redefine the universe itself. Before we plunge into the heart of a black hole, we have to understand its anatomy. From a safe distance, a black hole wouldn't seem all that remarkable. In fact, it would be completely invisible if not for the chaos happening around it. Many are surrounded by an accretion disk, a swirling, incandescent ring of gas, dust, and the shredded remains of stars that wandered too close. Friction in this disk heats the material to millions of degrees, causing it to glow so brightly it can outshine entire galaxies. These are some of the most luminous objects in the universe, known as quasars. This brilliant ring of cosmic debris orbits the edge of the abyss, a boundary known as the event horizon. Now, the event horizon isn't a physical surface you could touch. Think of it as a purely gravitational threshold. It's the point of no return. You can think of space-time as a flowing river. Far away, the current is gentle, but as you get closer, the current gets stronger, pulling everything downstream. The event horizon is the edge of a cosmic waterfall. Once you go over, the current of space-time itself is flowing inward faster than the speed of light. Every possible path, every direction you could try to move, now leads to the same place, the center. According to classical physics, this is why we can't see what's inside. Information is carried by particles, usually photons, and since nothing can escape from inside the event horizon, no information about the interior should ever reach an outside observer. It's a perfect cosmic prison sealed off from the rest of the universe. All we can do is watch from the outside, as observations confirm time and again that Einstein's theory is remarkably accurate in describing the space-time just outside the horizon. But it's inside, that hidden realm, where our journey truly begins, that the familiar laws of physics start to unravel.
Once we cross the event horizon, we leave the observable universe behind. From here on, our journey is guided by the math of general relativity. And according to that math, we're on an unavoidable collision course with the center. For a simple, non-rotating black hole, all the mass is crushed into an infinitesimally small point. For a rotating black hole, the classical solution describes a ring-shaped curvature singularity. Either way, you get the same core concept, a region of zero volume containing a finite, often immense, amount of mass. This is the singularity, a place of infinite density, infinite gravity, and infinitely curved space-time. It's a point where the equations of general relativity, the very tools we're using to describe this journey, produce nonsensical answers. They return infinities, which in physics is the universe's way of politely telling you that your theory has broken down. Physicists don't like infinities. They're a signal that the mathematical framework itself has reached its limit. So what does this actually mean? For decades, the singularity was treated as a literal answer, but the consensus among scientists today is that the singularity isn't a physical object, but a mathematical artifact. It tells us where general relativity fails, not what is actually there. The reason it fails is simple. General relativity is a classical theory. It describes gravity on large scales, but the center of a black hole isn't large. It's a realm where a star's worth of matter is squeezed into a space smaller than an atom. This is the domain of our other great pillar of physics, quantum mechanics. Quantum mechanics is the theory of the very small. It describes a world of discrete units, or quanta, and many physicists believe it's this fundamental discreteness that will rescue us from the infinity at the heart of a black hole. The singularity arises because general relativity allows matter to be compressed without limit, but a future theory of quantum gravity, one that unifies gravity with quantum mechanics, should prevent this. For example, in loop quantum gravity, a candidate for such a theory, space itself is made of tiny, indivisible chunks. In that framework, you simply can't have a point of zero volume because there's a smallest possible unit of volume. The classical singularity, then, is likely just a placeholder for a more complex and bizarre quantum reality. It marks the end of one chapter, Einstein's classical gravity, and demands the beginning of another, the strange and uncharted world of quantum gravity. The real question isn't what is a singularity, but what structure, governed by quantum gravity, replaces it. For a long time, the singularity problem was something physicists could mostly set aside. Since it was hidden behind an event horizon, it couldn't affect our universe. That all changed in 1974. In a stunning calculation, Stephen Hawking showed that black holes aren't entirely black. By combining quantum mechanics and curved spacetime, he discovered that black holes should glow with thermal energy. This is Hawking radiation. In simple terms, empty space is actually a sea of virtual particles that pop into existence in pairs and then disappear. But right at that black hole's event horizon, a pair can form where one particle falls in while the other escapes.
The escaping particle carries away energy, which means the black hole slowly loses mass. Over immense timescales, far longer than the current age of the universe, a black hole will radiate away its entire mass and evaporate completely. And this is where the paradox begins. A fundamental law of quantum mechanics is that information cannot be destroyed. Think of a book. If you burn it, the information isn't gone. It's just scrambled and encoded in the smoke, ash, and heat. In principle, you could piece it all back together. But what if you throw the book into a black hole? The information goes in, then the black hole evaporates. Hawking's original calculations suggested the radiation it emits is perfectly thermal and random. Its properties depend only on the black hole's mass, spin, and charge, not on what fell in. So when the black hole is gone, where did the book's information go? It can't be inside the now non-existent black hole. It didn't seem to escape in the radiation. It appears to have vanished. This is the black hole information paradox. It's a profound clash between general relativity and quantum mechanics. Resolving this isn't just about black holes, it's about the fundamental nature of reality. If information is truly lost, then quantum mechanics, our most successful scientific theory, has a major flaw. Most physicists find this unlikely and believe the information must get out. The challenge has been to figure out how. The resolution to the information paradox, which has been building for years, is as strange as the problem itself. A leading idea, supported by major theoretical breakthroughs, is that Hawking was right that black holes radiate, but the information isn't destroyed, it's subtly encoded in that radiation. To understand how, we have to introduce the holographic principle. Proposed by Gerard 't Hooft and Leonard Susskind, it suggests that all the information describing a volume of space is encoded on the 2D surface that surrounds it. In this view, all the information about what has fallen into a black hole gets imprinted on its two-dimensional event horizon. This idea got a huge boost recently. Physicists realized that to properly calculate the information in Hawking radiation, you have to account for all possible quantum histories of the black hole's evaporation. When you do this, a surprising feature appears in the math: contributions from what are called replica wormholes. These aren't traversable tunnels in spacetime, but rather complex connections in the calculation that link the black hole's interior to the radiation far outside. Including these in the math is astonishing. The result is that the radiation isn't random after all. It contains subtle quantum correlations that carry the information out. The math now shows that within these models, by the time the black hole has vanished, all of the initial information has been imprinted onto the outgoing radiation. Information is saved. This has profound implications for what the center of a black hole must be like. The singularity must be replaced by something else,
a complex quantum system that can store and process information. This leads us to several competing ideas. One proposal from string theory is the fuzzball. In this model, the entire region inside the event horizon is a tangled, vibrating ball of fundamental strings. There is no singularity, and in some versions of the model, no sharp event horizon. The information of what falls in gets woven into the fuzzball's vibrations and is then radiated away. Another hypothesis from loop quantum gravity is the Planck star. This suggests that as matter collapses, quantum pressure halts it at an incredible but finite density, creating an ultra-compact object. Due to extreme time dilation, it would look like a static black hole for eons, but could eventually bounce, releasing its stored information. So, if not a singularity, what is it? The truth is, we have a zoo of theoretical possibilities. We are standing at the edge of known physics, peering into a realm where the next great discovery awaits. Beyond fuzzballs and Planck stars, there are other wild ideas. Some models propose a gravistar, where space-time itself undergoes a phase transition near the center, creating a shell of exotic matter that resists total collapse. Then there are regular black holes, which are theoretical models that modify Einstein's equations to eliminate the singularity mathematically, resulting in a core with finite curvature. What's thrilling is that we may one day be able to test these ideas. While we can't look inside a black hole, different interior models could produce tiny but detectable differences in the gravitational waves from black hole mergers. As our detectors, like LIGO and Virgo, become even more sensitive, we might pick up these hypothesized signatures, giving us our first real clues about the quantum core. Researchers are also using quantum computers and machine learning to simulate simplified toy models that share key properties with black holes. While we aren't simulating actual black hole interiors in full quantum gravity, these studies help us map the behavior of particles under extreme conditions and explore what might be happening inside. This quest is about more than just black holes. It's about finding the holy grail of physics, a complete theory of quantum gravity. Black holes are the ultimate laboratory where gravity and quantum mechanics are forced to confront each other. Our journey has taken us from the brilliant edge of the event horizon to the paradoxical heart of a singularity, and finally, into the strange new world of quantum gravity. We began with a simple question: what's at the center of a black hole? The classical answer from Einstein was an infinity, a point where our understanding ends. The modern answer, born from the fight to save information from oblivion, is far more profound. It's not an end, but a new beginning. The center of a black hole is where the next revolution in physics is waiting. It may be a tangled fuzzball of strings, a bouncing Planck star, or something so bizarre we haven't even conceived of it yet. We don't have the final answer, but the quest itself has reshaped our view of the universe. It has taught us that information is fundamental, and that the fabric of space-time is more complex than we ever imagined. If you enjoyed this journey to the frontiers of science, be sure to like this video and subscribe for more deep dives into the cosmos. The singularity isn't the final word. As physicists often say, general relativity predicts its own downfall, and in the heart of the black hole, a new, better physics is waiting to be discovered. If you learned something new or found this topic as fascinating as we do, don't forget to like the video, subscribe to the channel, and hit the notification bell so you never miss a moment of space discovery. Got questions or thoughts about black hole or anything in the universe? Drop them in the comments. We love hearing what you think and might feature your question in a future episode. Until next time, keep looking up. The universe is full of surprises.